We are now moving into the second half of trigonometry, which begins from Chapter 7, Analytic Trigonometry. Chapter 7 is structured as follows. First, a review. We already went through all kind of different types of trigonometric identities in previous chapters, under different circumstances with different ideas. The purpose of 7.1 is to summarize them all and classify them accordingly. We're going to spend a little bit of time to prove them as well. And then in 7.2, we're going to introduce some more trig identities, namely addition and subtraction formulas, or equivalently speaking, the sum and the difference identities. 7.3 will turn out to be a continuation. We simply apply the addition and subtraction formulas, especially the addition formulas for the two same angles, then we end up with a double angle formula. Reverse that, we end up with a half angle formula, and so on and so forth. Finally, 7.4 and 7.5, we do some comprehensive problems. In order to solve an equation, usually you'll have to use all kind of things you have been doing so far up to that point, and then somehow find out a strategy to apply them. This is no exception. In 7.4, especially in 7.5, you're going to see a lot of very comprehensive problems that you have to combine pretty much everything about trigonometry to get done. Okay, let's begin. Let's begin with a reminder. This is the definition of the trigonometric functions: sine, cosine, tangent, and their reciprocals, cosecant, secant, and cotangent. Here is the first set of identities called reciprocal identities. Cosecant is one of a sine, consequently sine is one of a cosecant, and similar relationship between secant and cosine, cotangent and tangent. How do we prove those? Just apply the definition. Cosecant is r over y, as we see in this definition here, and divide both numerator and denominator by r. So what do you get from the numerator? R over r is just 1, and denominator is y over r. And what is y over r? The sine of theta. So what do we get? Cosecant is equal to 1 over sine. We completely proved it. How about the second one? Secant is defined by r over x, as we see here in the definition. Secant is r over x. And from there, we simply divide both numerator and denominator by r. In the end, what we get? R over r is 1. X over r is cosine. Eventually, we end up with secant is 1 over cosine. We can prove these kind of reciprocal identities like these, just starting from the definition, algebraically manipulate, and we just have a one-liner. The next set of identities is equally as simple in terms of proof, but in terms of implication, this one is far more important, especially this one. Tangent is equal to sine over cosine. Typically, I used to call it the formula number 2, implying that this is the second most important identity. Well, you don't have to agree with me. Not everybody agrees with me, but it will be close. At least up to chapter 6. Yes, it is. How do we prove those? Simple. Tangent is y over x, just by the definition. And then what do? Divide both numerator and denominator by same number, r. And then what do we get? Y over r is sine, numerator. X over r is cosine, the denominator. So we end up with tangent is equal to sine over cosine. Similar thing works for cotangent function. The proof is simple. Well, just one liner from the definition, but the implication is significant. Now let's move on to Pythagorean identities, and this one, especially the first one, cosine squared plus sine squared is equal to 1. I used to call it the formula number 1, implying that this is the most important trig identity. Now for that one, I have never seen anybody who is objecting to it. No colleague of mine. Everybody agreed to it. They don't call it formula number 1 just like I do most of the time, but they all agree that this is the most important. Now, how do we prove those? Not too difficult either, actually. This is all one-liner for each of them. What is the definition of cosine? Well, it's x over r. By the way, here is the reminder. Cosine is x over r, sine is y over r. So taking the square, we get x squared plus y r squared. Now, what is the definition of sine? That's y over r. So by taking square, we get y squared over x squared, y squared over r squared. Now, algebraically manipulate this. Just take common denominator. We have x squared plus y squared over r squared. But then again, what is x squared plus y squared? That's equal to r squared because we are doing this on a circle of radius r centered at the origin. So the numerator is r squared and denominator is the same. So what do you get? R squared over r squared is equal to 1. And that proves the first Pythagorean identity. By the way, this is called Pythagorean identity because originally this x squared plus y squared equal to r squared came from the Pythagorean triangle, Pythagorean right triangle. As you can see in this inscribed right triangle in this picture, or if I change the quadrant, some other picture, no matter what I have, x squared plus y squared is equal to the hypotenuse squared, r squared. And that plays a central role. So these three formulae are called Pythagorean identities. The other Pythagorean identities can be proven pretty much the same fashion. Put it into the definition and then algebraically manipulate. Manipulate you mean by just taking the common denominator. How about this one? 1 plus tangent squared. Well, tangent is y over x. So tangent squared is, of course, y squared over x squared. Now, how about 1? Well, in order to take the common denominator, you can express 1 as x squared over x squared. 1 is equal to x squared over x squared, and then put the numerators together. What do we get? You get x squared plus y squared over x squared. X squared plus y squared is equal to r squared. We already saw that. So what do we get? R squared over x squared. The definition of secant is r over x, so we end up with secant squared. The third identity can be proven the same fashion. Okay, let us move on to symmetry identities, which I call, but our textbook author calls them even odd identities. Why? Sine of negative theta is equal to negative sine of theta. That tells you the sine is an odd function. Cosine of negative theta is equal to cosine of theta. That tells us cosine is an even function. Same here, tangent is an odd function. So even odd identity, perfectly good name. I usually call them symmetry identities because they're talking about symmetry with respect to the origin or y-axis in terms of even odd, kind of like this. Let's see, you can see the graph of sine function. The red graph is an odd function because it runs to the origin and symmetric with respect to the origin. And blue graph, that's the graph of cosine function, and it's clearly an even function, symmetric with respect to the y-axis. And then here's tangent function coupled with sine and cosine. Even more so, the proofs follow the symmetry as well. And look at a couple of pictures, and they're a bit too thin. Okay, I like this kind of picture a little bit better. And left hand side we see the forward rotation. The right hand side we have backward rotation, clockwise rotation. So in the right hand side we are looking at sine of negative theta, for example, or cosine of negative theta, or tangent of negative theta. Compared with this negative theta value and those y value for the positive case, absolute value are the same. As a matter of fact, you see those two solid red triangles which are congruent, except that y value is going upward one way or the other way, downward the other way, which is of course taken care of by putting a negative sign. That's how we get the negative sign, negative y over r. So we end up with negative of y over r or negative of sine of theta. In case of cosine, it's all the same because x remains the same, as you can see in this pair of pictures. Horizontally, nothing changes. Tangent, well, I'll leave the detail to the students. Now, we have some more identities, but these are, I have to say, less important than the others, so let us go rather quickly here. Rotation identities, adding or subtracting pi over 2, sine becomes cosine, cosine becomes sine, tangent becomes cotangent, cotangent becomes cotangent, but the only thing you have to be worried about is pluses and minuses. Now, adding or subtracting pi, well, in that case, sine stays sine, cosine stays cosine, tangent stays tangent, but again, pluses and minuses will be a problem. Now, that's behavior is extended over to 1.6 complementary, 2 pi minus theta case, or supplementary case, pi minus theta case. Now, how do we prove those? Take a look at a couple of pictures. Oh, these triangles are a little bit too ugly. Okay, this one looks better. Please compare these two triangles. The solid triangles are standard triangles where the horizontal is on the x-axis, and then the dotted triangles are the versions obtained by rotating this solid triangle 90 degrees. Plus pi over 2, that's the first picture, and then minus pi over 2, that's going to be the second picture. And compare those. And compare this dotted triangle of the first picture and the solid triangle of the second picture. Are they the same? Yes, they are congruent. They are just symmetric. So x and y, r value, they are all the same, as a matter of fact. So the y value for the first picture is the same as the x value of the second picture, and vice versa. X value of the first picture is the same as y value of the second picture. So what we have, sine is y over r, cosine is x over r, and x is going to y is becoming x. Consequently, sine is becoming cosine, cosine is becoming sine. Of course, you have to be careful about the sign. Sign, I mean by pluses and minuses. How about adding or subtracting 180 degree pi? Yeah, like this picture a little bit better. Okay, subtracting pi, we end up with backward rotation, so it wasn't really good. I'd like to see a little bit more. Okay, this is a little bit more typical case. The others are all correct too, but this one is a little bit more typical case we can see. The first picture we have, and the second picture is obtained by rotating pi more, 180 degrees more. So what do we have? Well, we have a couple of triangles, of course, and they are the same as expected. So what do we have? X remains x, y remains as y, r remains as r. So sine remains as sine, cosine remains as cosine, and tangent remains as tangent, except, of course, pluses and minuses, which we'll have to be careful about. The other identities, well, conclusions are here, and the proofs are there. Just apply the first identity, rotation identity, for this one. Like, this is adding pi over 2 plus negative of theta, negative theta plus pi over 2, basically. So we have sine becomes cosine. And then apply even odd identity. We have cosine of theta in the end. And the other identities can be proven kind of same fashion. Apply the rotation identity first, and then apply the symmetry identity in the second step. But even better way to visualize those will be through geometry, actually. As you can see, let's say alpha and beta be the angle for A and B, and they must add up to 90 degrees, pi over 2. And sine becomes cosine, cosine becomes sine by simply changing a viewpoint. It's clearly visible here in this kind of acute triangle case.